Chapter 4, Section 5, Multiplying Polynomials. They're going to go through a couple methods of multiplication, which is really, we're going to go through the laws again, the associative, commutative, and distributive laws to work with multiplication and addition, really. When those two things come together, then we got some distributive property stuff. So here's kind of the summary of this section. The first one is probably the easiest, is multiplying monomials. Mono means single or one term. So in this case 3x is a one term or monomial, and this is a monomial. When you multiply these together, this is really just all multiplication. I could write that as 3 times x times 4 times x. And to do that, I'm using the associative law, which is changing the grouping here. I group this multiplication with these terms. Well, I can break that order of those grouping symbols with the associative law, since it's all multiplication. And then I can change the order with the commutative law. So I can say that this is the same as 3 times 4 times x times x. I can group them again using the associative, since it's still all multiplication, and I group this 3 times 4 together, and I get 12 times x, or x to the 2 power, x squared. So to multiply monomials, we basically just change the order of the multiplication. We put the coefficients together and do that multiplication to simplify that and get a simpler expression. So the examples they go through are like this. You still want to think about applying your rules of powers when you have like bases, like in example C here, 7x to the 5th times a negative 4x cubed, or to the 3rd power. Well, I can regroup that, change the order, right? I get 7 times negative 4, which is a negative 28. Good way to do this stuff is always determine your sign. I got a positive times a negative, I'm going to have a negative result or product. So I get a negative 28 times x to the 5th times x to the 3rd. To review that shortcut for powers, rather than have to write this out as x, 5 of those x's as factors, and 3 of these x's, and then add up all your x's, and you're going to get 8. Well, I can shortcut that by adding the exponents there when I have like bases multiplied. When I have a monomial or a single term against multiplying against to a polynomial or a multi-term deal, we use the distributive property, which is, like in this case, ax times the quantity x plus 3. I distribute that multiplication of x over all parts of the addition. So I end up with x times x plus x times 3. Usually in better orders, show it as x squared plus 3x. Well, it doesn't matter how many terms we have in there, that monomial will distribute over all parts of that addition. Terms are parts of an addition. I talk about this a lot. You may have less mistakes if you change this to an addition and stuff like that. So this is a very very nice tool. If you can draw a picture of anything in algebra or mathematics, you should draw a picture, and it illustrates this very well with rectangles here. So if I have this monomial times this binomial here, two-term expression, I can draw a picture of this with thinking of area of a rectangle. Well, if this is sides of a rectangle, x, and the other side is x plus 3, I'd end up with a diagram that looks like this. This is x plus 3. If I want to get this length of this line, and it says from here to here it's x, and from here to here it's 3, well, that whole line right there, that whole side of this rectangle is x plus 3 right here. Well, we distribute, we talked about, you end up with x squared plus 3x. Well, let's look at the area of each part of this. Well, if I made this break here, right, and I put this line up here. Basically I have a square that has a side of x. The area of that is x squared. This one has a side of 3, right? And what's this side right here is x. Opposite sides of a rectangle are equal. Well, so the area of this rectangle right here is 3x. So what is the area of this entire thing? It would be x squared plus 3x. This really illustrates that the distributive property works. It's kind of a picture to kind of prove it. And pay attention to these. This is a very important tool when we're dealing with these types of multiplications. I can draw pictures using area of rectangles. Usually it's going to be a rectangle. So they give us the law or the product. It says the product of a monomial and a polynomial. To get that, you multiply each term of the polynomial by the monomial. Or I would say use the distributive property and distribute over each term of this polynomial. Remember terms again, when we're talking about terms, the terms of this polynomial are x cubed, negative 7x squared, 10x plus negative 4. Terms are always parts of an addition. And once I have all addition there, I don't care so much, or I don't have to worry about order, because I can use the commutative law if I need to. In this case they don't need to, so they leave it as subtraction. But that's kind of determining some things. You know, the book and teachers do this a lot of times, is you kind of know the results, so you know when to go ahead and leave it as subtraction. One way to protect yourself against that is just use as a common way. When I write this kind of problem on my paper, I'll convert these subtractions into additions. Now multiplying any two polynomials, so we have multiple term expressions against another multiple term. Well, they look at a couple different cases here. If I have this binomial two-term expression x plus 5 and this binomial x plus 4, if I multiply those together, this is how I'd show that multiplication. Well, really what I'm doing is distributing this whole thing multiplied times everything. So I'm using the distributive law, and then I end up with this binomial times a monomial, and then I apply my monomial rules, which is the distributive law again. They show a change in order. I don't know why. You know, you could still distribute this way. Doesn't matter what order you do multiplication in, but we're used to seeing it in that form. So they use the commutative, change the order of these two multiplications here, and then they distribute again. So we end up with this new expression right here. But also these two middle terms here are like terms. In other words, if I put parentheses around 5x plus 4x, x is a common factor. I can factor out x, and that's the same as 5 plus 4 times x. I wish they would show that again, that really combining like terms is using the distributive property or law. Here's another example on how to do that. And you're going to learn some shortcuts rather than go through all these steps here. Really, I can take 4x times each term here and negative 3 times each term, and I'm going to end up with this polynomial. Remember, we're going to run into combining like terms. So here is a picture of this multiplication. They're doing that rectangle again, and you know, the important part, it's usually pretty easy to see once they draw it out. Drawing this from scratch might be a little more difficult. But if you think about sides, you know, when you don't have a known value here or a variable, that's x in this case. If this side is x plus 5, I'd say, well, I go down this side, I go x, and I think we get stuck on drawing pictures because we're going like, well, I don't know if x is longer than 5 or not. Well, it doesn't really matter for purposes of drawing this picture. We'll just say this length is x and this length is 5, And if that's true, then I know, even though I don't know what this length really is, that's variable, I could write an expression for the length of this side is these two things added together, x plus 5. Well, we do need to know that when I draw this picture, even though I don't know what the length of x is going to be, I know it's going to be the same length as this section that I decided to draw x as. So I end up with a square here. But remember, this side is x plus 4. And then I take the areas of these breakdown of all these rectangles in this big rectangle, right? And this section here, the area of that is x times x. This right here, this darker purple one, is 4 times what? What is this length? Well, hey, that's x, right? So 4 times x. And this one right here is 5 times x, because this has to be x. And this one, I actually get a number out because that's really a 4 by 5 rectangle. This is 4 and this is 5. So that's 20. So I get these four terms again, but these are the same kind of term. I can combine them with the associative property or add like terms and say this is x squared plus 9x plus 20. Well, when I got a trinomial or a 3-term polynomial and a binomial, they go through that same process. You're going to start seeing that there really is a shortcut. I can take x squared times x squared times 4, 2x times x, 2x times 4, negative 3 times x, and negative 3 times 4. And you're going to get basically what I said right here. But really what they're doing is they distribute to remember that we're just applying some laws that we had before. Then I combine like terms. So really what they're doing here is like long multiplication in a sense. If I have 321 times 12, that really is 300 is 300 plus 20 plus 1. And when I have a regular classroom, a lot of times I go through this multiplication method to show that this is really just the distributive property that does that. And I wish we would quit the shortcuts that we try to do with our grade school students and write it out similar to this. Is that this is really 2 times 1 is 2 ones. 2 times 20 is not 4. It is actually 40. And I could put that down below and add them. But in this case, they just put them in kind of numeric form again. And 2 times 300 is 600. So you get 642 when you multiply by that 2. And then this other one is 10 times 1, which is 10. 10 times 20, which is 200. 10 times 300, which is 3,000. And then you add those together. Like terms are kind of like, hey, these numbers have the same amount of places. I got hundreds and I got tens. I can add those together. It's a very nice way to think about how like terms work. So they talk about what that product means and how you can do that. They show a couple different organizational methods to multiply these things, which is very good to keep your work organized. What's nice about this is your like terms, if you do this correctly, will line up. So what they're really doing here again is to take the first part of this binomial right here, 2x, and you take it times each term in the trinomial. 2x times 3x is 6x squared. 2x times a negative, remember that term, we were talking about terms, parts of an addition. A negative 2x squared is a negative 4x to the third. 2x times 5x to the fourth is 10x to the fifth. Now why did they leave this gap here? Well, really what I have is I could have some things that are x to the fourth, and that's going to happen on our next multiplication. Well, they leave a space for each degree of the polynomial that I'm writing, right? Here's degree 2, degree 3. Let's leave a 0 here, or a blank for degree 4, degree 5, and so on. Well, this next line, the blue line here, is x squared times 3x, which is 3x cubed. Notice they put it in the x cubed, or the degree 3 term column in this sense, right? X squared times a negative 2x squared is negative 2x to the fourth, and x squared times 5x to the fourth is 5x to the sixth power. Now I can add up and down. I have my like terms lined up, which is only right here, and I end up with a negative 1x cubed. Okay, very nice way to organize your work when you do this stuff. Now, it says checking by evaluation. If I put a value in for the x, I should be able to do these kinds of problems and do it both ways. One is to just put it in the original, and later on when we get into equations, you're going to find a solution after you get done with these types of operations. And if you think you have a solution, I can go back to the original and see if it makes both sides equal. Then I know it's truly a solution. Well, what they're doing here to test or check really is to say, let's take a number which is easy to deal with, like 1. If I cube 1, that's easy. That's 1, right? Square 1, that's 1. Multiplying by 1 is easy, right? So they do this. They put it in the original. They say, well, let's put x in for, or 1 in for x, and see what we get. In this case, they get 56. Make sure you follow order of operations. Well, when we distributed, we ended up with this new expression, which was this one right here. It should come out to exactly the same number, or else we made some kind of math error, or we made a multiplication error really in this distributing the multiplication over these two things. Then they go into some technology around that with graphing calculators, which we're definitely not focused in on this class, but that's a pretty straightforward section. Good luck, and hopefully you've got a proctor arranged by now, and if you haven't, you need to start emailing me, and we need to work on what that's going to be. I did get some emails. Remember, I think if you're around the Wenatchee campus, Susan Atkins, or Sudi, she likes to go by, is usually only in her office from 1 to 7 in the afternoon. That's her proctoring hours. There is on announcement, there's proctoring information. There's actually a form you can submit if you want to set up proctoring with her on the Wenatchee campus. So make sure you read all that stuff. Phone calls are not always the best way to get a hold of some instructors, and you still got plenty of time. So get that done, and I'll talk to you later.